Hello everybody, welcome back to another Gregorius Maths video. Today I'll be doing Topology 1.3, namely we'll be looking at subspaces. Okay, let's get right into the video. I'm not messing around today. Let me turn on some light, so I can see, because my vision is not the best. Okay, anyway. So, say we have some topological space T. Okay, for example, Rn, okay, so that's an example of a topological space, right? Then, the subspace topology, okay, the subspace topology on S, a subset of T, okay, is defined as follows. Okay, so how do we define it? Well, of course it's got the word sub in it, so we're thinking of subsets immediately. So this is our topological space T. What we do is we pick some open set in T, call it U, okay, such that its intersection with S is an open set, okay? So the open sets are defined as the intersection of some open subset of T. Okay, so, okay, a set is open in the subspace topology, okay, if it is, says open if it is U intersect S for some open U in T. Okay, so basically the drawing. Okay, I don't think I've defined this very precisely, to be honest. But if we have some T, we pick some open set U in T, so it's open in T, and we have our space S, then this intersection is an open set in the subspace topology. Okay, and we refer to S as a subspace of T. Okay, cool. I think if you see some examples, then you know what I mean. So, for example, if we have the integers. Okay, so if we define n in the integers, okay, so n is in the integers, that means that n is equal to the open interval about n minus a half to n plus a half, okay? Oh, sorry. Intersect the integers, okay? And now we're seeing from the definition that the integers is a subspace of the real numbers, okay? And every single n in the integers is open. But doesn't this remind us of the discrete topology? Yes, it does. We call Z a discrete space. Okay? That means, from a proposition that I proved in the last video, any function whose domain is the integers is continuous. Okay? For goodness sake. Ah. Oh my goodness. Okay. So if we take one more look, if we have the one sphere, okay, basically the set of all x, y such that x squared plus y squared equals 1, or the unit circle, okay, however you want to call it, I'm going to call it the one sphere, okay, is a subspace of R2. So for example, we have our one sphere, okay, and we have the open ball of radius 1 about the point 1, 1. Well, that's going to look like something like that. Basically, yeah, it's going to look nothing like that. It's going to intersect it here. Okay? So, for example, this part here, okay, is going to be open. For example, that's a terribly explained, but I think you're getting the idea. Okay, so now that we've seen a couple of examples, why don't we look to define continuity in a more sensible manner, kind of using these subspaces. So if we have a function f from S to t, where S and t are topological spaces, and it's continuous. Okay. Now, if we're given some Q, Q is a subset of S whose image under F, okay, so its image under F is contained in R, a subset of T, okay? So we have some Q, a subset of S, whose image under F is contained in a subset of T, okay? Therefore, we can restrict F to Q. So the new domain is Q and it maps onto R. If Q and R are given the subspace topologies, okay, then the restriction of F and Q, however you say it, I don't know. Basically this restricted function from Q to R is continuous. Okay? This seems very wordy, but thankfully it's not too difficult to prove. So the proof goes like this. Okay, so let's pick P, a subset of R. Okay. Now, that means that the pre-image of P under this restricted function is equal to Q intersect the pre-image of P. Okay? Now, because P, we're going to let P be open in the subspace topology, let U be let U, a subspace, a subset, sorry, not subspace, a subset of T be open. So we're letting U be open. Why are we doing this? Because now this means that Q intersect the preimage of P is equal to Q intersect the preimage of R intersect U. Okay? From the definition. Yes, okay. Which equals Q intersect the preimage of R intersect the preimage of U, which equals Q intersect the preimage of U. Why? Well, hold on, let me write this on a new line. Q intersect the preimage of U. Why is that so? Well, we remember that Q is a subset of S whose image under F is contained in R, but if its image is contained in R, then if we take the preimage on both sides, that means that Q is contained in the preimage. So therefore we can go from here to here because Q is completely contained in there. Okay. And now, since F is continuous, okay, this means that the preimage of U is open in T, right? Because F is continuous, this follows from the definition of continuity, okay? And therefore, the preimage of this restricted function, okay, is continuous. Why? Well, we've got our subspace Q intersect the preimage of some open thing, basically in T, okay? And from the definition of the subspace topology, this is open in the subspace topology, meaning that the preimage of an open set, because P was open, because we wrote it like this, P is open, and now the preimage, okay, is open, therefore F is continuous. Oh, I mean this function here is continuous. Okay, so for example, if we have the function which maps the 2 sphere into R3, okay, well this is continuous because it's just a restriction of the mapping of the identity map, which looks like this. Okay, it's just a restriction of that, therefore it's continuous. Okay, and now I shall define a basis. Okay, so the definition of a basis is as follows. A collection of sets, okay, let's call it B, okay, is said to form basis for a topological space T, okay, so a collection of sets B is said to form a basis for some topological space T if for every B, let's call it lowercase b so as to avoid confusion. For every B in the basis, okay, each open subset of T can be written as a union of can be written as a union of elements of B. I didn't really need that, but okay. Basically, each subset of T can be written as a union of elements of B. In fact, I really didn't need that. Okay. So, if we give a quick example just so that that's clear. If we had let's go back to our boy B. Let's say it's equal to 0, 1. Okay, let's say it has the discrete topology. The basis of B is 0 and 1. Okay? Because every single subset of B can be written as a union of those two. Okay? That's basically all it is. What's the point of looking at these bases? Okay, well, again, it's about continuity. We can look at these, we can look at continuity from the view of bases. Okay? So if we have a function f from s to t, again, they're both topological spaces, is continuous. Okay? If T has a basis B, okay, and for all lowercase b in the basis, okay, the preimage of B is open in S. Okay, so it's nearly the definition of continuity, except we only have to check that every element of the basis, the preimage of that, is open in S. Okay? Now this is more of a logical proof than mathematical, I would say. It kind of follows from the definition, really. Yes, the black pen works. Let's go. Okay, the proof is, say we have some open Q, subset of T, okay? This means that Q can be written as, this means that Q can be written as unions of elements of the basis, okay? Therefore, the preimage of Q is equal to the preimage of the union of elements of the basis, okay? Which is equal to the preimage of one, which is equal to the preimage of the element of the basis, and in union the preimage of another element of the basis, etc., etc. And seeing as the preimage of every element of the basis is open in S, and because by the definition of a topological space, arbitrary unions of open sets are open. Therefore, by talking, I've completed the proof. F is continuous. Okay, and thank you guys for watching. I'm very, very excited to finish this video because now we can look at connectivity and compactness and other properties of topological spaces. I'm so excited. Goodbye.